In this video, we're going to do a really short introduction to acids and bases, and we will specifically be talking about some of the health applications of these compounds. So this is the pH scale. You're all probably pretty familiar with it. We've talked about this a bit, and here is our pH of 0 all the way up to our pH of 14. And if we remember from our class, the pH is a mathematical description of the H plus or hydronium ion concentration in solution. So this right here is what makes an acid acidic. And the pH is just the negative log of the concentration of this acid component. And so different compounds, different liquids can have different concentrations of this. So hydrochloric acid, if it's 1 molar hydrochloric acid, it has a pH of 0. Your stomach acid is also HCl, but it's a little bit diluted, and so it has a pH of around 1 or 2. Citrus fruits are closer to 2, vinegar and wine and coffee 3, 4, 5. Milk is a bit acidic, and then water is neutral. Our blood is a little bit basic, not much basic, but a little bit. And then there's baking soda, milk of magnesia, ammonia, soap, bleach, and drain cleaner. So these are all examples of something that you would find in your house that is that pH. So it should give you an idea of how the pH scale kind of works. Over on the right side is where we have a higher number and a lower concentration of the H plus. And these tend to be slippery and taste really bitter. Whereas acids tend to taste really sour. We have a low pH that corresponds with a higher concentration of the H plus. So our definitions of acids and bases can vary depending on which school of thought you're talking about. So over here, this is the Arrhenius definition, and this down here is the Bronsted-Lowry definition. Now, I personally do not necessarily care that you can name one or the other, but I do want you to be able to recognize an acid or a base using one of these definitions. So all acids are Bronsted-Lowry acids, and then some acids are also considered Arrhenius acids. So here's the thing about the Arrhenius definition is it has to really happen in water because it's increasing the full-on concentration of this here. So you put some acid into the water and you immediately get a whole bunch of H plus or hydronium. Whereas bases, what they do is they increase the concentration of the hydroxide. And so you put some base in the water and you immediately get a whole bunch of hydroxide in your water. Whereas the Bronsted-Lowry definition, this talks about specific proton donation and acceptance. So here's what I mean by that. So if you have your compound that has a proton on it, an H, that can go off to maybe float freely in water and hook up with another water molecule and make the thing more acidic. So that hydrogen ion is given away. So this would be the acid. And whatever compound is that accepts that hydrogen ion would be the base. So in this case, we have ammonia. Ammonia is a weak base, so if you've used ammonia cleaner in your house, it's a little bit of ammonia gas dissolved in water, and this would accept a proton from water and generate some hydroxide. And so even though ammonia doesn't have a hydroxide on it to just dissociate into the water, it still increases the concentration of this of the hydroxide here and leads to a higher pH. So these are the two ways in which acids and bases interact with a solvent like water. So a bit more vocabulary. We will talk about this when we look at specifically buffers. But for right now, I just want to point out that every base has a conjugate acid, and every acid has a conjugate base. So what that means is once you remove a proton from an acid, you now have its conjugate base. And once you add a proton to a base, you get the conjugate acid. So here is the picture version of that. This is kind of the formula that you could follow where you have an acid and that equals the H plus and its conjugate base, whereas the base and the H plus is the conjugate acid. And we generally, by convention, just put the acid or base on the left side of the arrow and the conjugate on the right side. So this would be the pair would be like this, and this pair, and here we have our acid and our base reacting with each other, and the acid donates that proton and becomes a conjugate base, and this base here accepts the proton and becomes the conjugate acid. So let's look at this example problem and see if we can identify the conjugate acid-base pair. So this here is acetic acid. This is the acid that's in vinegar, and this is water. And this is the anion, this is the acetate anion, and this is our hydronium ion. So here we can see that we have the acetate part, and then we have this proton here. So that means that this is probably acting like our acid because it's going to kick off this and increase the H plus in the water or donate the proton to something. So if this is our acid, that means this is our conjugate base. And that makes sense because now it's a negatively charged thing that could accept a proton. So it could act like a base. So this is our acid and this is our base. And that means that that water must be acting like the base here. So this water molecule, this oxygen has two lone pairs on it and it can accept this proton here and make H3O+. So if we wanted to look at what that would look like if we were to draw out Lewis structures, we have our parent acid, that's the acetic acid, and the base, which is the water. And you can see once you've gained your proton, you're now a conjugate and a conjugate base. I also want to talk a little bit more about the autoionization of water. So water molecules can dissociate into an H3O plus and an OH minus, or an H plus and an OH minus, so the proton and the hydroxide. So in a sample of pure water at 25 degrees Celsius, this happens about 1 in, I think it's like 1 in 100 million or 1 in a billion molecules do this or something like that. So we have a concentration of this is 1 times 10 to the minus 7th. And then these are equal. So pure water is neutral. Its pH is 7. And these are equal to each other. So all aqueous solutions at 25 degrees, if you multiply these two numbers together, it's always going to equal 1 times 10 to the minus 14th. So that means that if you know this, you can get this number here. And if you know the hydroxide concentration, you can get the hydronium ion concentration. So all aqueous solutions at 25 degrees Celsius, this here is true. And then if everything is equal, if these concentrations are equal, that would be neutral, pH of 7, and they're both the same. Any other pH, these are not going to be the same as each other. They won't be equal to each other, but if you multiply them together, you will still get this number here. Okay, so we can talk about weak and strong acids and bases. And this is really very similar to our idea of an electrolyte. So remember that strong electrolytes are compounds that dissociate completely in water, so something like NaCl, sodium chloride, but also strong acids and bases like hydrochloric acid and sodium hydroxide. So if you have a sample of hydrochloric acid, what you really have is some water with a whole bunch of protons and a whole bunch of chloride ions, because these do not stay stuck together in the water. And with sodium hydroxide, a strong base, the same thing is also true. However, weak acids and bases do not fully dissociate. So in this example here, this would be like vinegar. Vinegar, which is a solution of acetic acid, has some of our acetate anion, some of our proton, but then it also still has some of our initial acid compound that hasn't dissociated yet. So we can write this with two arrows, and we have a bigger arrow pointing to this side here because there's more of this in solution than there is of the compound that's been broken up. So neutralization reactions, these are really important because this shows how a compound can react with an acid and produce some sort of different product. And now you've actually seen this in lab. And if you've ever taken an antacid for anything, what you're doing is you're consuming a base in tablet form, which is probably going to be something similar to a carbonate, like you could have a magnesium or a calcium carbonate. You chew up this base and the compound can neutralize some of the acid that's in your stomach. If you have a disease called gastroesophageal reflux disease, or GERD, this is a very common cause of heartburn because the acid rushes up back into the esophagus. And so consuming something a little bit basic will neutralize that acid. So we saw this in our carbonates lab. And if you have your calcium carbonate reacting with hydrochloric acid, you get carbonic acid here and calcium chloride. And then your carbonic acid here can be neutralized. It can form water and carbon dioxide. So this here, this is that compound that's in oyster shells and our Dungeness. And if we get too much acid in our oceans, they can start to degrade the shells of our oysters. So these types of reactions are all over the place in environmental chemistry and in health. And so it's important to understand how these compounds can react with each other.